Today's lesson is about solving using the square root property of equality and the imaginary number. Why do we learn about the imaginary number? The imaginary unit allows us to find solutions to many equations that do not have real number solutions. This may seem weird, but it is actually very common for equations to be unsolvable in one number system, like the real number system, but solvable in another, more general number system, such as the complex numbers system. We'll learn more about how complex numbers and real numbers relate when we move on to the next section. But imaginary numbers are not just there so mathematicians can do things that they're not supposed to be able to do. There's an enormous use of complex numbers, numbers that consist of a real part and an imaginary part, in applied math and physics. They occur quite naturally in the study of quantum physics. They're useful for modeling periodic motions such as water or light waves, as well as alternating currents. So all this time you were not allowed to square root a negative number, but now we are. Mathematicians defined the square root of -1 as the imaginary number I. If I is the square root of -1, let's do some algebra to understand what I squared is, or I cubed, or I to the fourth, and so on. I squared would be I times I, so square root -1 times square root -1. That could just be written as the square root of -1 squared. Because a square root and a square are inverse operations, they undo one another and we are left with the radicand, the number under the radical. So I squared is -1. I cubed could be I squared times I. If I squared is -1, I cubed is just -I. I to the fourth could just be rewritten as I squared times I squared. If I squared is -1, that makes I to the fourth 1. I to the fifth could be rewritten as I squared times I cubed. We already know that I squared is -1, and I cubed is -I. So I to the fifth is positive I. I to the sixth could be rewritten as I squared times I to the fourth. I know I squared is -1, and I to the fourth is positive 1. So I to the sixth is -1. I to the seventh could be rewritten as I squared times I to the 5. I squared is -1 and I to the 5 is I. So I to the 7 is -I. I to the 8 could be rewritten as I squared times I to the 6th. I to the 8 is equal to 1. Do you see the repeating pattern? What do you think I to the 9 will be? What about I to the 10? I to the 11? I to the 12? Imaginary numbers keep following this pattern. In geometry, you worked with simplifying radicals by finding a factor that is a perfect square of the number that's being square rooted. A perfect square meaning 1, 4, 9, 16, 25, and so on. So let's look at number 1. 8 is not a perfect square, so we cannot just find the square root and be done. But there is a perfect square that is a factor of 8. And keep in mind, if there were multiple, we would need to choose the largest. The perfect square that goes into 8 is 4. So I can rewrite this radical as a product of radicals that are equivalent. The perfect square factor of 8 is 4. 4 times 2 is 8. Now square root the piece that you can and leave the one you can't. The square root of 4 is 2, so we remove the root and then drop the root 2. What about the square root of -16? We can also rewrite a negative number under a square root as a product with -1. The square root of -1 is I. The square root of 16 is 4. Even though I is not a variable, we write it after the number when written as a product. I know that 9 goes into 72, so let's try that. Before I get any further, I notice that the piece that I'm supposed to leave alone, the root that is supposed to already be fully simplified, that's not actually simplified. We were able to simplify that earlier. So you could directly plug in 2 root 2 instead of root 8. Or to avoid this problem altogether, you could notice, okay, if this is not fully simplified, that means I didn't take out the biggest perfect square factor of 72. 72 is actually 36 times 2. And if you had done it the other way, you'd still get the answer, but if you left root 8 in your answer, that would be incorrect. 120 has a perfect square factor and a negative in it. So let's rewrite this as a product. First, I'll take out the negative. We write the I in front of the root. We don't want to write anything after the root that's not under it, because sometimes if you get sloppy with your roots, then it's confusing to see what is under the root and what is outside of it. The biggest perfect square that goes into 120 again, we write the number in front of the imaginary number when written as a product. Could we break down root 30 anymore? The only possible factors of 30 that would be perfect squares would be 4, 9, 16, 25, and none of those go into 30. So we are done. When is a quadratic equation a good candidate for solving by square root property of equality? That is when b is equal to 0, or if your variable is inside of a quantity squared, similar to vertex form. For number 2, let's begin by thinking about this problem intuitively. What number squared is equal to 9? That would be 3. Is there another number that when you square it, it's also 9? What about negative 3? So if the equation is x squared equals 9, x could be 3 or it could be negative 3. So when we solve by using the square root property of equality, meaning we've isolated the term that is squared and now we square root both sides, the square root of 9 outside of an equation is just 3. But once we are solving in an equation, we have to include that it could have been negative 3 as well. So we write plus or minus, meaning positive or negative 3. Let's solve number 3. The term that is squared is completely isolated, so let's square root both sides. I could rewrite the square root of negative 9 as the square root of 9 times the square root of negative 1. The square root of 9 is plus or minus 3. The square root of negative 1 is I. Keep in mind, this is two answers, x equals positive 3i and negative 3i. For number 4, the squared term is not yet isolated, so we need to do that. Treat it just like you would solve an equation where the x squared is just an x, but then at the end we'll need to use square root property of equality. Now that the squared term is isolated, square root both sides. X is equal to positive or negative square root 1 over 12. The problem is because this whole fraction is rooted, that means there's a root in the denominator. So I need to rationalize the denominator. First, I'll split the root. Root 1 over 12 is the same as root 1 over root 12. Square root of 1 is 1. The square root of 12, wait, we can actually simplify that. 4 is a factor of 12. So let's rewrite square root 12 as square root 4 times square root 3. Unfortunately, we still have a root in the denominator, which means we'll need to rationalize by multiplying by root 3 over root 3, a special form of the number 1. Root 3 times root 3 is root 3 squared. Root 3 squared is just 3. And your answer is plus or minus root 3 over 6. For number 5, is the squared term isolated? Not quite entirely. We have a 4 being multiplied by x squared. So divide first, and then square root property of equality. Anytime you square root both sides of an equation, you have to write plus or minus. You have to take into account the positive option or the negative option. The negative that's in front of this fraction can belong to the numerator or the denominator. I'll put it in the numerator and separate that root so that we can rationalize. The square root of negative 1 is I, and the square root of 2 cannot be simplified, so we need to rationalize it to get it out of that denominator. To rationalize, we multiply by a special form of the number 1. Root 2 times root 2 is the same as root 2 squared, which is simply 2. For number 6, is the squared term isolated? Yes, the term, which is a group now, that is being squared, is all by itself. So let's solve with square root property of equality. First of all, we just used the square root property of equality, which means we have to put plus or minus. The square root of negative 18 could be rewritten as the square root of negative 1 times the square root of 18. You may notice that 18 has a perfect square factor, so we can simplify root 18. Rewrite root 18 as root 9 times root 2. The square root of 9 is 3. We write the 3 before the I and the I before the root. Our last step is to isolate x. I always write that number in front so the plus or minus is in between the two terms. For number 7, is the square term isolated? Not yet, so let's do that. Now is it isolated? No, we still have 2 being multiplied by the quantity that is squared, so we need to divide both sides by 2 first. Now the squared term is isolated, so let's use square root property of equality to solve. Don't forget your plus or minus, and we can simplify this radical. There's a perfect square that goes into 44. Remember, that's 2 different answers, and even though the form may look complicated with a root or a plus or minus sign, this is the most precise, accurate answer. You could also find a decimal approximation of these answers, but that would be an approximation, not the most accurate form. If you plugged in 2 plus 2 root 11 into a calculator, you would get 8.633, and so on. And if you plugged in 2 minus 2 root 11, you would get negative 4.633, and so on. Because you are not allowed to use a calculator, you won't be asked to give decimal approximations, but if this were a real-life problem, decimal approximations might give you a better sense of what your answer is coming out to be. And that is solving quadratic equations with square root property of equality.